So welcome everyone, and today we are going to talk about more in respect of the eigenvalue. And today we want to talk about the degenerate case. So the first question that comes to our mind is that what is degeneracy? So degeneracy is defined by repetition of eigenvalues, and this means if you have a matrix, let's say a 3 by 3 matrix, it might happen that you can have one of the eigenvalues as 1 and the other 2 equals to 3. That is the second eigenvalue, and the third eigenvalue is also, both of them are 3. So let's take an example. Here we denoted our operator, that is a matrix, in the finite dimensional vector space as a 3 cross 3 matrix with elements like this. And to find the eigenvalues, we are going to use this equation over here, that is this one. So this will give us our eigenvalues, if you recall from our previous lectures, and I'm denoting the eigenvalues with omega. And if you do a bit of algebra after this, that is, you calculate the determinant, you try to simplify the things, you will finally arrive at something like this over here. And from here you can see that I have 2 minus omega. I can factor out omega over here. This will be omega minus 2 equals to 0. But this 2 minus omega can be written as omega minus 2 by factoring out a minus 1. So factor out this minus 1 and multiply or divide by both sides. So the final result will be omega minus 2 whole squared times omega equals to 0. So this equation 1 gives us two options, that is omega equals to 0 and omega minus 2 whole square equals to 0. Now omega minus 2 whole square equals to 0, this guy is the culprit for our degeneracy, because you might think that okay, I'm getting just 2 one time, but no, this omega minus 2 whole square means omega minus 2 and omega minus 2 equals to 0. So this means either this guy is 0 or this guy is 0, and from there you get omega minus 2 equals to 0 two times. So the 2 is repeated over here, and graphically, if you think of it, if you have some x minus 2 whole square and you want to plot it in the xy axis, it will intersect the point 2 one time, but this is actually the same root, but since this is a quadratic equation, we expect to have two solutions, because that's the fundamental theorem of algebra, right? A equation with degree n will have n roots. So it's a 2 degree of equation 2, equation of degree 2, and it should have two solutions. So here the solutions are just repeated. So we say our eigenvalues omega are 0, 2 and 2. Now there seems nothing wrong so far, but why we are calling it degenerates will be clear when we try to find the eigenvectors. So let's try to do that. So let's find the eigenvectors now. Okay, let me just use another color. Eigenvectors. And first we will consider the case where omega is just 0. So if omega is 0, then you will have 1 minus 0 over here, 0, 1, 0, 2 minus 0, 0, and finally you will have 1, 0, 1 minus 0. And here you will have x1, x2, x3, right? These are coming from our past lectures, that is the eigenvalue stuff like this. So this is just a matrix representation of this abstract equation. So if I end on the right hand side, you will have a 0 vector. So if you just now multiply this thing, the first one will give you x1 plus x3, the second one will give you 2x2, the third one will give you x1 plus x3. 0, 0, 0. And from here you can conclude that x1 is equals to minus x3 and x2 to be 0. So the eigenvector that will correspond to omega equals to 0 will be given by x1, since our x2 is 0, so put a 0 over there, and x1 is equals to minus x3, so that also means x3 is equals to minus x1. So something like this. And if you normalize it, so let's now, if you normalize it, then this will be just 1 by square root over 2, 1, 0, minus 1. So nothing wrong there or nothing suspicious there. So let's now try to go for omega equals to 2. And also note that when we are considering omega equals to 0, which is a non-repeated eigenvalue, you can see that like we discussed in our past lectures, if you have a 3×3 system, then the value of n is 3, and you should have two equations that will give you some unique information, and one of the equation will be just redundant, that is, there is no need for that equation. And here you can see that that is from here. Okay, let me just highlight it again. From here, this equation and either this one or this one serves that purpose. So we'll now consider what happens when omega equals to 2. And this is our degenerate eigenvalue, that is 2 is appearing 2 times. So let's try to see what happens if you try to do that. So again, we'll have 1 minus 2, 0, 1, 0, 2 minus 2, 0, 1, 0, 1 minus 2. And here you will have x1, x2 and x3. And 0, 0, 0. So here finally you will have minus 1, 0, 1, 0, 0, 0, 1, 0, minus 1. And finally you will have, if you multiply, minus x1 plus x3, 0, x1 minus x3 equals to 0, 0, 0. And from here you can conclude that x1 is equals to x3. But notice that this equating these two guys will just give us 0 equals to 0. And again, this third equation also means x1 equals to x3. So you can see that we are expecting to get at least two unique equations that will give us some valuable information. But here we have just only one, right? I mean, not one, actually two. But since you have the eigenvalue 2 repeated 2 times, again doing for the third eigenvalue 2 will also lead back to these equations. So this is where the idea, this is where the degeneracy is located. And this 0 equals to 0 means over here, if you recall from our past lectures, our x2 is arbitrary. So the eigenvector for omega equals to 2 will be this will be x1, x2 is arbitrary, and x3 is just x1, right? So this guy is arbitrary, x2, and x1 and x3 are equal, so instead of x3 you can just write x1 over here. And now what you can do, you can just, to normalize it, you can just take x1 equals to 1, x2 equals to, let's say, 1 for simplicity. So this will just be one, 1 and 1 over here, and our square root of 1 upon 3 over here. So this is after you do the normalization, taking x1 equals to 1 and x2 equals to 1. But since our x2 is now arbitrary, what we can do is that we can change the value of x2. So let's denote this with another color so that you can understand better. So again, if you just, let's say now I can want to have x2 equals to let's say -2. So this will be now 1, -2 and 1. And if you normalize it, you will have 1 upon square root over 6, and this will be 1, -2, 1. See that we have 3 eigenvalues, and we mentioned earlier that for each of the eigenvalues we should have a unique eigenvector, and these eigenvectors should be mutually orthogonal to each other. But you can see that this is not the case when the eigenvalues gets repeated. That is, omega equals to 2 is repeating here, and we are not getting 3 eigenvectors, rather 2 eigenvectors, and one of the eigenvectors that corresponds to omega equals to 2, that is the repeating eigenvalue, has one entry as arbitrary. This means what this means is that, so let me write the significance. The significance is that this arbitrariness induces extra degree of freedom and they define an ensemble of vectors, that is, they define, by they I mean degeneracy, define an ensemble this means just a collection of vectors that are perpendicular to the first one and they lie, that means they lie on a plane that is perpendicular to the omega equals to 0. That is, this degenerate vectors lie in a plane perpendicular to the vector omega equals to 0 for this example. And in fact, if you notice carefully here, that is the which is not the normalized eigenvector, just look at this. Here, this eigenvector will actually depend on the ratio. By ratio, I mean the ratio of x1 by x2. Or you can always say x2 by x1, that's your choice, but let's write this again. So for omega equals to 2, we had x1, x2 and x1, right? So what we can do now is that we can divide it by x2. That is, 3 of the rows will get divided by x2, and we'll have x1 by x2, 1, and x1 by x2. So these entries over here, that is this one, okay, let me choose another color, it's not that good. The entries over here and the entries over here are actually dominated by the ratio, that is, they're determined by this ratio. So this clearly, each distinct choice of these ratios give us a distinct double of orthonormal eigenvectors with eigenvalue 2. So here we have 2, that is omega equals to 2, repeated 2 times, and we call it a 2-fold degeneracy. Oops, sorry, let me just cut that out. So it's a 2-fold degeneracy. Now A very schematic way of seeing the geometrical picture will be something like this. Let's say this is the omega is equals to 0 eigenvector, something like this, and all the eigenvectors corresponding to omega equals to 2 will be like this. So there is this infinite amount of eigenvectors for each choice of x2. So whenever there is degeneracy, you are kind of getting some degrees of freedom, and because of that, you are not in a very restricted space. By space, I don't mean a vector space, but you are not in a very restricted situation where these eigenvectors will be mutually orthonormal or orthogonal, whatever you want to call it. So each of these, so let me just denote this line, that all this family of vectors, or you can say the set of vectors, will correspond to omega equals to 2, and this is lying in a plane that is perpendicular to the non-degenerate eigenvector, and all of them will be mutually orthogonal to omega equals to 0 eigenvector. And degeneracy, the reason we are interested in degeneracy, because we can see degeneracy in our hydrogen atom. That's a famous example of degeneracy. And when we want to deal with hydrogen atom in quantum mechanics, you see that there is degeneracy, and having these ideas will help you to understand that physical phenomena as well. And this will be it for today, and thank you.